morning, dear participants. The subject of this short course, certification course, lifelong learning base course, is to make an introduction to the valuable topic, stress analysis, but not on the paper, using the tools of virtual environments, the environments of such as Inventor, environment of fusion. At the beginning, I have a short presentation for being at the safety side, although I'm sure you know what is stress, what is strain. But yes, make a quick review on the basic definitions. And then start to deal with the things in the virtual environment. Okay, in engineering, it is the main issue to deal. What is the subject, the main subject in engineering? Design. Okay, at the design stage, the main objective is that, determine the critical values of the components. If it is a pressurized vessel, the critical value is thickness of the shell. If it is a bolt connection joint, say the critical value is the diameter of the bolt. Or if the diameter has been fixed, then the other issue to deal, how many bolts are needed? Or say that the chassis of an automobile, whether that chassis is going to be strong enough under the action of the loads. Okay? Or it is a bridge, while the heavy loads, vehicles are crossing the bridge, whether the bridge going to be still strong and can safely be used. And most of the engineering designs, we aim to have the material of the object complete in its elastic region. We do not desire to want plastic deformations. Okay, at the design stage, to be able to find the critical values, diameter of the shaft, thickness of the pressurized vessel, cross-sectional area of the structural elements of the structure, truss bridge, etc. Yes, you know the method. It is stress analysis. Well, instead of talking about or using forces, atomic bonding forces, it is much more convenient. To be able to make the results more general, we use forces per unit of area. But saying force, I mean intermolecular bonding forces. Here, for instance, it is like a potato, you see, and that is our object. Imagine what it is. It may be a truss bridge, it may be chassis of an automobile, or whatever it is. Imagine, in any shape. It is under the action of the loads, if it is say that our system, the rest of the universe will be the surroundings. These are the loads exerted, onto our object by the surroundings. We have some tools, of course, between the system and its surroundings. We have some tools. Thanks to the existence of these tools, surroundings can apply the loads. If the contact area between the tool and the surface of the object is small enough, then say that idealization, it is a concentrated force. If not, if the contact surface between the tool of the surroundings and our system is a finite size area, considerable area, we say that over there is a distributed load. Okay, and the other famous load, is to consider in some cases, it is a bulky object, heavy object, is the gravity force, weight of the object. so on and so forth. Okay, we know the forces while the object gonna be being used. The object going to be under the action of such laws. And then, well, the main question is that whether the object, to its all the components, to its all the joints, and to its main parts, gonna be strong enough under the action of such a loading, such loads. How about the atomic bonding forces? If atomic bonding forces reach the limits, then you know the result. First, going to be plastic deformation, yielding will occur, and then, well, strain hardening enables us to increase the load, but there is a limit, of course. If that limit is exceeded, then fracture will occur. Okay, in doing this, you know the famous technique. We imagine cut the body at a certain cross section, and then at the cross section, writing the equations. If the object is in equilibrium equation. If not, then the equation of motion. Find the atomic bonding forces. And then, well, since it is more convenient to study, we resolve the atomic bonding forces, resultant of the atomic bonding forces, into the components. Well, the component of the atomic bonding forces, resultant of the atomic bonding forces, it is perpendicularly oriented with respect to the selected cross section. It is called normal force, and if we divide the normal force to the area of that surface, we obtain normal stress. The other component is the tangential component. If we divide the tangential component of the atomic bonding forces to the area of that surface, it is in consideration while we are looking for the atomic bonding forces at that cross section, then this means the result is shear force. The component is called shear force. Shear force per unit area is called the shear stress. Okay, well, for stress values, we know the mechanical limits, mechanical properties of the material. For steel, there is a limit. For copper, another limit. Okay. If the limit is exceeded, the atomic bonding forces cannot balance the applied loads and unavoidable to have the fracture. Okay, it's going to be broken. Yes, normal stress, shear stress. We use Greek letters to say normal stress sigma, to say shear stress tau, you know. This is not the theory course, you know, say very brief review. Okay. For being at the safety side. And you know, within the object, it is something like that, like a potato. Well, this is an important question, you know. Beforehand, it was quite time-consuming thing. Okay, we have an object, but at which place within the object, at which point of the object, the stress gonna be maximum under the applied loads? Well, you know, to answer at that time, beforehand, there was no computer, no flat environment. Well, okay, at least, well, some simple cases, for instance, object is a beam, okay? For the beam, well, you know, atomic bonding forces, shear force, bending moment, and then, well, to be able to find at which point, at which cross section it's gonna be maximum stress, gonna be maximum, well, we pull out the shear stress curve, bending moment curve, and then after seeing that it is the maximum value, then for that maximum value, calculate the stress. It can be done, but for some geometries. If the geometry is quite strange, difficult, okay, to its shape, and it is under the action of not one-dimensional loading, but 3D loads, then yes, it was a challenge at the time. Well, which point the stress is maximum? Well, to answer that question, of course, scientists, engineering scientists, academicians, well, deeply studied on the answer of such a question. And in that, well, the students in school found some advanced courses, advanced elasticity, theory of elasticity, advanced plasticity, theory of plasticity, master and or PhD level courses. But today, of course, we have software, Inventor, Fusion, etc. Life is not so difficult for the designer today, thanks to the existence of such software. Uh, okay, but don't forget, well, today, the software of today at the background use the outcomes of those valuable academical studyings. Well, in the structure of Inventor and that of Fusion, at the background, we have the outcomes of theory of elasticity, theory of plasticity, and the famous analysis method, finite element. Yeah, yes, well, it is like a potato, okay, and then at which point the stress is maximum. You know the famous method, well, with discretization. If the problem is the one not so difficult, you can solve the problem on a piece of paper using integration technique. To be able to find the differential equation, first, and also to say that stress at where? At this point, at this point, well, making the discretization, we assume that we divided the body into infinite number of what? Rectangular prismatic elements. And then we isolate one of them. Here it is in this figure can be seen. And then for that infinitesimally small element, okay, then normal atomic bonding forces normal to surface per area is the normal stress. The other one's shear stress. Okay, and then, well, since it is infinitesimally small, can say that it is the stress at the point. Practically, it is like a point, tiny, infinitesimal small element. Okay. And then, yes, if it is in equilibrium, write the equilibrium equations for the infinitesimal small element, and then find the differential equations, and then be able to solve the equations. But if the geometry is complex, if also loading is, well, the one, we have some oblique forces, okay? Bending effects quite complex, not in coplanar, but again, oblique moment vectors we have. Then today, yes, analytical solution quite difficult, but today, instead of dividing the body into infinite number of infinitesimally small elements, we divide the object into finite size elements. And there is a theoretical course in engineering curricula. The famous name, common name of the course is finite element analysis. Well, in mechanical engineering curriculum, yes, the code of the course is MEC 413. Probably at least some of you have already taken that course, okay, and your background is quite strong in theory. In this short course, after in few minutes, I'm going to complete my reviewing part, and then use the tools of Inventor first, and then those of Fusion. Yes, such environments, the theory is finite element theory. Okay, software today have user-friendly tools, just in form of push buttons. But since in using the tools of the software, there are some tricks and some details to know, that's why we organize such courses, okay? Under the guidance of the tutor, professor, teacher, okay? It is better to study on the things, okay? Not alone by yourself. Because, well, mainly it takes greater time. You should make lots of search in Google, for instance. What is this? What is that? More time. But if you attend to such a course, okay, the person will guide you, teach the things at a shorter time with little effort. Dear students, today, well, I don't know, it depends on your um, enthusiasm, interest. We may use 3 hours, okay, this session of the course. But, well, although the course is an introductory course on stress analysis, but even for making an introduction, 3 hours won't be sufficient. So, if you say that, Hocam, okay, we gathered all the things, that's okay for us, then okay, say that one session only. But after hearing me that, well, the next session may be on this and that, if you say that, yes, Hocam, well, we are deeply interested with the second session as well, then okay, we may say, I don't know, your exam program. If your program is suitable, going to be suitable for the second session, it may be held on next Saturday, the same time. Then yes, well, making the considerations beforehand to the presidents of the societies, yeah, yes, we plan to plan this course as the one maximum with 2 sessions. If you say that, yeah, Hocam, well, there are lots of other things, further details, 2 sessions couldn't be sufficient, can address a semester course, full semester course. Well, one of them is offered by me, computer-aided design. It is, code is MEC 533. You're welcome to that course, okay? For the further parts, deeper parts of the subject. Okay, well, that is the question. I'm keen on answering the question because I know from my experience, it is in the mind of the students, in general speaking, beginners. Beginner, but not to say freshman student, beginner for such things to his or her level. To be able to determine the property of the material, mechanical property, in stress analysis, we should know the mechanical property. What is the limit for the material? Material is steel, material is copper. What is the tensile limit? What is the yield limit? What is the fracture limit? Well, to find the answer of such questions, under laboratory conditions, we perform tests. Okay, using standard shaped and sized specimens. And famous test, tension compression test. Okay, experimentally. Standards say that, yeah, well, specimen is to be something like that, size, geometry, etc. And then by using a test machine, in our engineering laboratory, you can find such a machine, tensile compression test machine. We have such a system. Okay, well, this is the specimen, and well, if it is tension test, the gripping ends of the mechanism slowly applies the forces, increasing the magnitude from 0 to the maximum 1. Meanwhile, the processor and sensors, okay, continuously sense the elongation and the, thanks to the existence of load cells, the magnitude of the applied force, and all of such things are recorded. Within this box, there is a computer, microprocessor, etc., and software. And then in today's technology, in the display of computer, we can see in the famous curve, stress-strain diagram. Okay, yes. For a ductile material, it can be generalized. Well, if the material is ductile material, steel, for instance, the most commonly used famous ductile material. Okay, copper ductile, aluminum ductile material. The other group, brittle material. For ductile material, when we plot the curve, which curve? Strain stress curve. Along the y-axis, we have stress values. Along the x-axis, strain values. Okay, we find the curve in this form. The first part of the curve, it extends from the origin to such a point, is linear, you see. Well, this part of the curve corresponds to the behavior of the material. It is completely elastic. Whenever the load is removed, okay, then body can turn back to its initial form. Elastic behavior, like a spring. But there is a limit for this part. It is called yield limit. If this limit is reached and little bit exited, then well, the rest will be plastic deformation. Okay, although we didn't increase the load drastically, but can have a very great elongation, stretching, we say yielding occurred. Okay, most of the designs we do not desire to have plastic deformations. Okay, for instance, it's a bridge, truck across the bridge pass through, and then bridge deformed plastically, deflected. Never desire to have a deflected bridge. Okay, but some applications, which one say press works? Yeah, press work is to change the shape of the material permanently. Okay, apply the force using press machine and then set the shape of the sheet metal to the shape of the template mold. If the case is such a thing, then of course, well, we consider the things, the material is in plastic region. Okay, now trying to take a pointer. Yes, after yielding, atomic bonding forces going to be greater in size. We say strain hardening. And so thanks to such an hardening, we can furtherly increase the loading. But when this limit is reached, then, yeah, well, it is the limit, ultimate stress. And then if you attempt to furtherly increase the load, then the unavoidable result is that fracture will occur. Okay, performing such an analysis, we apply uniaxial loads to the ends of the specimen. That is the question. Yeah, yes. In elastic region, the famous proportionality constant is called modulus of elasticity, Hooke's law. Okay, and capital E is the modulus of elasticity. This is valid in elastic region. Okay, although we perform the test, yeah, well, applying uniaxial load, that is the question. How can we use the results of such a test, for instance, yield limit, in designing the object? It is going to be not under the action of uniaxial load, but 3D load system. And the object is not in the geometry of specimen. It is like potato. It is geometry is in general quite strange. That is the question in the mind, I know. While the student taking the introductory course said that, yeah, hocam, okay, we know the mechanical property, but it has been determined for this simple case, uniaxial loading. Yeah, well, on the answer of this question, scientists, engineering scientists, deeply studied, of course, how many years ago. And yes, the short answer is yield criteria. Yes, we have two commonly used yield criteria. Thanks to such yield criteria and outcome of such deep analysis today, yes, in virtual environment, can say directly something. Not a matter, it is in which geometry. At which point, what is the stress? whether over there will be a failure. Atomic bonding forces reach to elastic limit or even reach to the fracture limit. Yes, now for ductile materials, two alternative failure criteria we have. One of them is Tresca failure criterion. The other one is von Mises criterion. In Tresca criterion, maximum shear stress is considered. Okay, and say that Tresca yield criteria says that if at a point maximum shear stress is equal to the shear stress that has been determined during the test, uniaxial test, standard test, then over there yielding will occur. But von Mises criterion, not shear stress, but say that, energy. Okay. Well, first, how about the other one? The other, for brittle materials, we have similarly two criteria. One of them maximum normal stress criterion, the other one Morse criterion. Okay, Tresca shear stress theory. Well, Tresca says that at the end of deep theoretical analysis, of course, and performing some verification tests, then in Tresca criteria, we say that, okay, first principle stress minus third principle stress divided by 2. Okay, not a matter the geometry is what, not a matter which load we have. Okay, we first determine the principal stresses, first and the third, and then half of it. If half of the difference is equal to tau sub y is the maximum shear stress, yielding shear stress, okay, determine it under laboratory conditions via uniaxial loading. Then if this equality is valid, then well over there yielding will occur. Okay. Yes, of course, well, can be approximately written. What is the yield limit for shear stress? Although in uniaxial test we determine yield limit for normal stress. Well, half of normal stress is almost equal to shear stress. So, well, write sigma y divided by 2, and then, yes, this is the Tresca theory, mathematical expression of Tresca theory. Sigma 1 minus sigma 3 is equal to sigma y. If it is the case, then over there, yielding will occur. That is the Tresca failure theory. The other one, von Mises. Von Mises, considers the distortion energy. It says if at the point the maximum distortion energy is equal to the distortion energy determined during uniaxial loading under laboratory conditions, over there yielding will occur. Okay, to be able to calculate the distortion energy, well, that is the final form of the analysis on the paper theoretically. Well, distortion energy is equal to, well, Poisson ratio plus 1 divided by 6 times Young modulus, in the parentheses, the square of the differences between the principal stresses, first principle, second minus third principle minus first principle. Okay, for uniaxial loading, under laboratory conditions, we perform the test. You know, the second principle stress 0, third principle stress 0. So, well, the distortion energy expression gives us the distortion energy, in such a case, uniaxial loading. Okay, for uniaxial loading, distortion energy can be expressed, since the other principal stresses are 0, in this form. Okay, and then, yes, according to von Mises criterion, if the distortion energy for uniaxial test is It is at the right hand side of this equality. And at the left hand side, we have the distortion energy at a certain point within the body. If these are equal to each other, then at the point there will be a yielding. Yielding will occur at the point. Okay. Now today, since for ductile materials it is more common to use von Mises yield criteria, in the default configuration of Inventor, it is the selected criteria. If we run the software and output the results, can see the von Mises stress. Yeah, yes, this term you see in the end after making the cancellation, the final form of the mathematical expression of the criteria is equal to this one. Yeah, well, at the left-hand side, we have a strange term, square root of the squares, sum of the squares. But at the other end, what we have the yield limit. Uniaxial test, yield limit. So, well, since it is equal to stress, yield limit stress, yielding stress, then this term is a stress value. It is called von Mises stress. Okay? Well, program outputs von Mises stress. Of course, in using today's software, after selecting, of course, can inform the user not only on von Mises stress, but also first principle, second principle stresses, or while the stress, okay, in the at the point where that point the selected surface is perpendicular to x-axis and the stress is in the y direction, or vice versa, etc. All of that, and also strain values can be dropped throughout the body, not a matter which point. Okay, completed my brief reviewing part, and then yes, dear students, this course aims to educate you on not the tools of SolidWorks, CATIA, Siemens NX, but the calculation tools of which, not all of them, only stress analysis tools of Inventor. And well, not today, but if you say that, okay, Hocam, one more session is valuable for us, then can say that next week, okay, can focus the attention to the tools of fusion. Yes. Mm-hmm. Today, no. I'm not free in the afternoon. Well, I must be in my office when I have a work to deal. Okay. Okay then. Well, I'm going to deliver a few sentences and then have a break. And after the break, then say that work, classwork. Yeah, in Inventor, in the structure of Inventor, dear students, this is a screenshot. It may be the simplest problem to deal, okay? While using the classical stress analysis tools of Inventor, I took this screenshot. After the break time, yes, I'm going to say that, okay, then first use the classical tool, stress analysis tool of Inventor. And then, well, the other tool, today for a few years in the structure of Inventor, we can find not only the classical tool of Inventor, but also, well, most capable tool can be used for almost any kind of engineering problem. Its short name is Nasran in CAD. Well, why still, although today for a few years we have the module, it enables us to use that famous software Nasran. Why software keen on keeping the classical stress analysis tool of the software in this version, and probably in the following versions, we're going to have both of them, because the classical tool is easier to use. Okay, Nasran is complex to use, and in the structure of Nasran, that part, well, the things require more attention, and well, the user should know some further details, some tricky details. Okay, it is not an easy case. That is the main reason. But well, be aware in using the classical stress analysis tool of Inventor. Well, the problem may be only such a one, special case, not all the cases. Well, if the temperature within the body is uniform, means there is no heat transfer across the body. And the other condition to satisfy, material is to be completely in elastic region. If at least a point plastic deformation will occur, then well, cannot believe the results output in the end by the software. While the classical tool of Inventor valid to use, applicable to use, if the material gonna be in elastic region. This is an important restriction. Okay, no heat transfer, no energy storage, while temperature is uniform. Okay, and also constant. Temperature uniform and constant. Okay, and the material gonna be in elastic region. And another restriction, okay, for this tool of the software, well, the object is to be under static conditions. Static stress analysis can be performed using the basic classical tool of Inventor. Okay, but the other one, Nasran, the open form of this famous word is that finite element analysis software. Its name is from NASA structural analysis. Well, the software has been for the first time developed and started to use 1960s in NASA. Okay, in NASA it has been coded and structured. But in 1971, magical thing occurred, and then, well, for instance, Inventor, thanks to enabling, okay, allowed by NASA, well, added a valuable module saying Nasran where in CAD, which CAD, Inventor, Nasran in CAD. Okay, today, thanks to that allowance and agreement between NASA and Autodesk, then we have for a few years that powerful calculation tool in the structure of Inventor. Okay, you know, all of you have already taken 113, MEC 113, and you know, since our university is eligible to use the products of Autodesk, you are also eligible to use all of them. But you know, it requires membership. You know how, just access to the page of education community of the company, Autodesk, and then fill in a form, say that you are a METU student, etc., and then you're going to be eligible thereafter. You're going to have the rights of the member of the society, association. And then, yes, install Inventor, that's okay, in your personal computer. But for having the module, Nasran module, after installing Inventor from the same page, over there you can see the list of the products of the company. Find Nasran in CAD option and download Nasran in CAD. After downloading that software, that product, can find Nasran in CAD tab as embedded in the structure of Inventor. Okay, Nasran capable, yes, to use for such kind of problems. Not only linear static analysis, but also nonlinear static analysis. Nonlinear static analysis means yielding will occur and then material will be in plastic region. Backlink may be studied in Nasran. Thermal analysis, yes, can be studied. To find the temperature distribution within the body, we can use Nasran. Well, not only to find temperature distribution, but also to say something whether atomic bonding force is going to be strong enough, sufficient to balance the external forces. I mean, in short, thermal stress analysis. What else? Frequency analysis, module analysis to determine resonance frequencies, and some other difficult problems. Impact mechanics can be studied. Well, there is such a table to make a comparison between the classical tool of Inventor and Nasran CAD. If there is a cross, then that software cannot be used for that purpose. The other strong software today is again the product of the same company, Fusion 360. It is a cloud-based software. Okay, the main part of the program is not in the personal computer or workstation. It is at the host computer of Autodesk. That is the cloud for this software. Well, similar to Nasran, Fusion is also capable to perform almost all the engineering analysis. Static stress analysis, nonlinear stress analysis, resonance frequency, determining resonance frequency. And another tool, it is not at present available in the structure of Nasran. It is just today, in short, can say that a tool for enabling the designer to design the object as a sustainable object, sustainable solution. There is a shape generator facility. That facility exists in the classical part of Inventor and also in Fusion. Well, program may offer, yeah, well, you're wasting the material over there. No need to use extra material over there. Okay, that part may be empty. Okay, it can be emptied. No need to have such a solid material over there. So empty that space. Of course, if we obey to this recommendation, then the material going to be saved. Okay, and also the object going to be quick response object. If we decrease if the material is less, then it is inertia going to be smaller and it's going to be quick response. The other issue to know, allowable stress. Okay, well, we determine the limit under laboratory conditions, but for being at the safety side, instead of making the design using such a limit, we divide the limiting value, yield limit for instance, by a factor depending on the case. If the loadings are dynamic loads, if at the place the people do not obey to the restrictions, well, designer says that that object can be used by, at the same time, maximum 10 people. Some countries, all the rules are strictly obeyed. Okay, that comes from the culture and also education system of the country. But other countries, people say that, don't care, although it is written 10, well, why not? I can also use 11%, 20%. If the attitude in the country is like that, then designers select a greater factor for being at the safety side. So safety factor, factor of safety. Factor of safety requires well-educated designers. Okay? Experienced designers, not arbitrarily selected. Factor of safety is selected by the senior designer. Okay, considering all of the listed things. And then yes, in performing the stress analysis, it is the other parameter. Yeah, have a look at this, the factor of safety. Whether the object over there is safe to its atomic bonding forces, so the object can be used safely, securely used. Find the factor of safety distribution and then say something. Okay, dear students, break time, good news. After the break, continue. 10 minutes, I think, sufficient. Tamam.
demedim. O yüzden son anlatmış oldum.